Hey, North, Mr. Euler here. We're going to talk about orbital filling diagrams and quote-unquote exceptions. If you keep in mind the fact that the atom it doesn't want anything or doesn't try to do anything, it doesn't have any awareness, obviously, right? It's just a bunch of charged particles that are obeying the laws of physics. So it really can't have an exception to those rules because then everything would fall apart, right? The reason we have what we call exceptions is more because our rules are kind of overly simplistic. And so I use the word exceptions kind of carefully because I want to make sure that we're not thinking that the atom is like breaking any rules. It's really that our rules don't perfectly match what happens in real life, right? An atom has to follow the laws of physics. It's just attraction of oppositely charged particles and repulsion of negatively charged particles. That's essentially all that there is to what makes an atom do what it does, right? But it's so complex because obviously you can get into quantum physics and stuff where we're talking about an electron is kind of like a probability wave and not really a particle at all. And so it is very complex, and our rules that we follow describe the patterns that we see, but they don't describe them perfectly because they're kind of overly simplistic. So I just kind of want to emphasize that point, that the atom isn't really breaking any rules per se. By the end of the video, we should be able to do a orbital filling diagram. I'll show you how to do that and kind of be able to kind of identify the different kind of rules that govern the placement of electrons within the atom. Before we do that, though, I want to talk about this idea of stable versus low energy. Stable means chemically unreactive. The noble gases are stable because they don't interact with other atoms very much. That's not really what we're talking about here. What we're talking about here is the position of electrons within an atom. We're not talking about how atoms interact with other atoms. And so the term low energy is better. And to help you kind of make sense of that, because it's a little bit more of an abstract idea, maybe think of the analogy of like a satellite orbiting the Earth. You have to input energy to get it up to an altitude where it can orbit, right? If it were to lose energy, it would come back to the Earth if it were to slow down, right? So a low energy state is actually closest to the object that it is attracting it, right? The same is true in the atom. The nucleus attracts the electron because they're oppositely charged, so the lowest energy state is actually closer to the nucleus because it would require energy to pull apart two particles that are attracted to each other, okay? And nature is going to gravitate towards the lowest energy state. And on this picture, it's sometimes referred to as an energy well. Picture like a ditch or like a valley. Again, it takes energy to get the electron out away from the nucleus, and so the lowest energy state is going to be closest to the nucleus, and that's represented by those electron energy level lines. This diagram kind of breaks it down into sublevels, the S, P, and D sublevels, which is what we're going to talk about today. So we're going to place electrons in particular spots within the atom, and this is kind of similar to that Bohr model, putting electrons on certain rings, but it kind of goes into a little bit more detail. So there's a couple of rules that kind of govern the placement of electrons. One is called the Aufbau principle, which says that the lowest energy fills first, and this is consistent with what I was just saying. Electrons are going to go to the lowest slot that's available to them, okay? So if you have one electron, it's going to fill the 1s orbital. If you have a second electron, each orbital holds 2 electrons, so it's also going to go in the 1s orbital. The second rule is the Pauli exclusion principle, which says that the electrons have to have opposite spins. Now, an electron is not really a particle that's actually spinning. Again, it's like a wave. It's a lot more complex. But we represent this with the up arrow and the down arrow. Another rule that we kind of use to kind of identify where electrons are is Hund's rule, which is that they spread out before they pair up. So if we put more electrons in, they have to go to the next highest energy level, which is the 2s. And then if you add an additional electron, they have to go to the 2p, but there's 3 orbitals. So if you add 3 electrons, they have to spread out before they are going to pair up. You're not going to pair up two of these and then have one by itself. The reason being that all 3 orbitals are at the same energy level, the same height or distance from the nucleus, and so the electrons being all negative are going to repel each other. They're going to fill those 3 equal spots evenly. If you were to add additional electrons, then they start pairing up. because they're gonna pair up before they have to go up to a higher energy level. Now, let's look at an example and connect this to the periodic table. If you're kind of like reading the periodic table from left to right, you're adding an electron to each subsequent atom, right? Let's pick the first transition metal, I think it's scandium, to kind of look at as an example. We at this point we're at 2p, so we're right here, right? We filled the 2p sublevel. The next electron would have to go in the 3s, right? And then the next electron would have to pair up the 3s, okay? Continuing on the periodic table, now we're at the 3p's, which is the next highest energy sublevel. Again, they spread out before they pair up. So working your way across the 3p's, you now have this. This would be like argon, I believe, is in this position right here. Continuing to add electrons, you go to the 4s, right, which is the next highest in energy level. And then the next highest, notice the 3d is actually a little bit higher than the 4s, but below the 4p, which is why the next row that you hit is the 3d. So notice that you're in the fourth row, but it's n minus 1. It's the third energy level. The 3 is the energy level. The d, the letter, is the sublevel, and the lines represent orbitals. The d sublevel has 5 orbitals, and so it can hold 10 electrons, okay? But we're only going to stop at the first one here, and so you're just going to have one electron represented in the 3d sublevel. So that's an example. You could do this with any any element on the periodic table. Notice that, I need to get that bar to disappear. Notice that down towards the bottom, when you hit 6s, it jumps down to 4f. Those two rows at the bottom are inserted in between the 6s and the 5d, or the 7s and the 6d, respectively. A couple of terms to kind of just be aware of. Make sure you have these written down in your notes. You'll come across them periodically. Paramagnetic is when you have unpaired electrons. Diamagnetic is when you have all paired electrons. You can kind of think of it as the magnetism is dead, or it dies when they're all paired up. So any element that has unpaired electrons would be affected by a magnetic field. Okay, so now we can get to these exceptions, quote-unquote exceptions. There's two that you really need to be aware of. They're copper and chromium. So copper is one away from a full 3D orbital, right? So your electron configuration or your electron orbital filling diagram would look like this, right? Where you have one left in the 3Ds. What copper does, it achieves a slightly lower energy state if it moves one 4s electron up to the 3D and it fills the 3D and leaves the 4s unfilled. That's for whatever reason, that's a lower energy state than having it as shown. So how it's shown here is actually not how copper exists in nature. It moves that one electron, the 4s, up to here. Okay, the same thing happens with chromium. So chromium has 4 electrons in the D sublevel. Again, it achieves a slightly lower energy state if it moves one electron up to half fill, so you have all 5 of those orbitals filled with 1 electron each, and then you have the 4s1. So in nature, what we find is that chromium atoms have a 4s1 3D configuration. The little bit of like additional energy to get that electron up to the next energy level kind of like pays off, so to speak, in achieving a lower state overall, a lower energy state overall, and so that's what they do. Those are the 2 exceptions that you really need to be aware of. This picture is great. I love that it shows the pattern. If you add one more electron, it just continues to add to the 3Ds, right? But then you hit chromium, and now all of a sudden it's worth it, so to speak, to move that one electron to fill the 3Ds, and so you have 6 orbitals, really 5 Ds and 1 S, that are half filled, and that's a lower energy state than having this one full and this one not full. Same thing at copper, right? Notice that copper, there's like this jump. It goes from 3 full orbitals to 5 full orbitals because you're kind of stealing one, so to speak, from the S. And you'll notice that copper actually, a common oxidation state for copper is copper 1. And looking at this, you can actually make sense of that. Why does copper often form a copper 1 ion? Because it has one 4s electron, and it will lose that 1 electron and become copper 1. It will also become copper 2. A lot of the transition metals will become positive 2 ions, and that makes a lot of sense too because they all have 2 electrons in the 4s orbital that are lost because they're at the highest energy level. And so you end up with a +2 charge, and that's common in the transition metals because of that. We're going to come back to this with electron configurations a little bit down the road. So this is Mr. Earler signing off.